Okay, so we're going to finish up where we started on last Wednesday by looking at how a substituent can affect the electronic properties of the benzene ring. And so I guess I'll just call this substituent effects. And we're going to look at two different cases. The first one is phenol. So phenol or hydroxybenzene is classified as an electron donating group. So I'm going to abbreviate that EDG, electron donating group. And so we're looking at how the substituent affects the electron density of the benzene ring. So I'm going to clean up these pi bonds a little bit. Because what we do on the rest of this board here is look at resonance structures. So again, this term, electron donating group, we're comparing it relative to a hydrogen itself, for example, just regular benzene. So the hydroxy group, when compared to benzene, is an electron donating group. And what that means, the electron pairs on the oxygen can donate into the ring, and it's going to donate in a very specific way. And that's really our what we want to understand for the rest of the lectures in this semester regarding the reactions of aromatic chemistry. So the electrons are pushed into the ring, and again, if you sort of cover that up, that resembles an enol. So now we see that there is electron density at the position right next to where the hydroxyl group was bonded. We can draw another resonance form where the electron density goes here. So if we count 1, 2, 3, 4, the lone pair will be in the 4 position. And then we're going to have one more resonance form where now the lone pair is right next to the hydroxy group, but on the other side. So substituents that have basically a heteroatom with at least one lone pair of electrons can donate those electron pair density into the ring. So you see that here, a lone pair, a lone pair, a lone pair. What this means, compared to benzene, this electron ring is enhanced with, or this aromatic ring is enhanced with electron density. So we would say it's electron rich relative to benzene. So with my green marker, what I want to do is point out on this molecule. See how these lone pairs end up here, here, and here? This group, electron donating group, donates specifically to those positions. So if we look, the relationship between the group and this green arrow, that's a 1-2. A 1-2 relationship, an ortho relationship. Hopefully you guys can see that. So here, it's at the 4 position. So 4. A 1-4 relationship is called para. P-A-R-A. So an electron donating group donates the electrons to the 1-2 or 1-4 position. That's called an ortho-para director. And that's going to become important to us when we start looking at the reactions. I'm going to turn this camera a little bit. That does not seem to have helped. I don't know, can you guys see that? That green? So this is an electron donating group. Now the next group we're going to look at is electron withdrawing, and it makes the aromatic ring have less electron density when compared to benzene by itself. So we're going to look specifically at nitrobenzene, we have an aromatic ring with an NO2 group. So what's going to happen now, this atom that's bearing a positive charge is going to pull the electron density out of the ring. It's going to do it in the same fashion you see the charge up here, except instead of having a negative charge, we're going to have a positive charge at the 1-2 and the 1-4 positions. So instead of electron density going into the ring, it's coming out. So this carbon here is going to end up with a plus charge. We then shift those pi bond electrons onto oxygen. So this plus charge is going to remain on nitrogen, but we're creating a plus charge here and a minus charge there. So again, the electron density comes out of the ring. It ends up on oxygen. We get a plus charge here. We can shift these electrons again. The plus charge migrates from here to the 4 position. We can draw the last one, where the plus charge migrates from here to that position. So there's those resonance forms. So notice that in comparing them, in the electron rich, you have a lone pair at the 2 position. The electron deficient, you have a carbocation. So again, negative, positive, negative, positive. So what I want to do here in red marker, I'm going to put those arrows where we see that plus charge. Because those positions are electron deficient with, maybe what I'll do with instead of a green arrow, I'll use an orange marker. Wherever there's not a red arrow, I'm going to put an orange arrow. That is a 1-3 or meta, M-E-T-A relationship. So electron withdrawing group is called a meta director. And so we want to understand the reactivity between electron donating and electron withdrawing. So you really need to understand resonance forms at this point. And so what we're looking to do is, when we do reactions of an aromatic ring, we classify the substituent as electron donating or electron withdrawing. If it's electron donating, where these green arrows are, that's where we say the substitution is going to happen. If it's electron withdrawing, where these orange arrows are, that's where substitution happens. The substitution has to happen at a place where there's some electron density. So that's our first whiteboard. Any questions on this before I go ahead and erase it? So on this next board, what I want to do is talk about relative positions. If you have a mono-substituted benzene, basically you would name the molecule as benzene with whatever that substituent is. What we talk about here, relative positions, this is only for di-substituted. Only for di-substituted benzenes. And there's three different scenarios that we're going to encounter. So ortho, meta, and para. These are the designations you'll see in your book. This is called ortho or O, meta or M, para or P. Ortho is 1-2. Meta is 1-3, and para is 1-4. And again, these are only for di-substituted benzenes, and these words relate to the relative locations of the substituents to one another. So what are some examples? So this molecule would be called 1,2-dimethylbenzene. So a common name would be O-xylene. So this would be more like an IUPAC name. This would be more like a common name. So a 1,3 relationship. This would be 1,3-dimethylbenzene or metaxylene. Again, given that we're in this online situation, if you need to look something up, say during the exams, I mean, you obviously can do that. So you really don't have to memorize any of these things. So our last scenario here would be the 1,4 relationship, and this would be paraxylene. So I've started off fairly straightforward, where both of the substituents are the same, so they're a little bit easier to name. Hopefully that is straightforward to understand. What I would like to do, one exercise, is look at how would you then differentiate these constitutional isomers from one another using NMR spectroscopy. So you have the 1,2, the 1,3, and the 1,4. So let's do some chat box exercises here. Here I'm going to write 1,3C. Maybe let's do that first. So for the ortho isomer here, how many unique carbon signals would you expect to see for this one? If you want to enter a number in your chat box, we'll see if we can agree on something. Anyone else want to respond? Okay, we've got a couple more showing up here. So we have a healthy dose of 4. Maybe what I'll do here is identify them in red. So when I look at this molecule, I see a plane of symmetry. So maybe I'll number them. So the methyl groups, those are equivalent. We have these aromatic carbons. So the plane of symmetry makes those mirror one another, so we get 4. Now keep in mind what the NMR experiment is. Maybe what you can do in the chat box next, since these are all isomers, what's the molecular formula of all of these? So maybe write that in the chat box. How many carbons, how many hydrogens total? So it looks like we got C8H10. So the benzene ring itself is 6, 7, 8 carbons. hydrogens, we have 1, 2, 3, 4 on the ring. 3 from that methyl group, that's 7, 3, that's 10. So they're all going to have CaH10. And again, just visually looking at it, you have a ring, you have 1, 2, 3 pi bonds, so that's 4 degrees of unsaturation. And we're doing this exercise here to help us differentiate between the different relationships. So for the metaxylene, how many unique carbons should I write here? So this one's 5. Again, there's a plane of symmetry. So even just by doing this thought experiment, if we were given the actual carbon spectrum, we would say this has 5, this has 4. So we can use this to differentiate them. So what about for paraxylene? What number should I write here? Okay, so we have 3. Even though my pi bond's drawn a little bit kilter. So that's a good spot. The answer is 3. You have symmetry here. And then you have another plane of symmetry bisecting orthogonal to that. So the methyl groups are 1. These carbons are 2. And then the ring carbons are all 3. Because you have those 2 orthogonal mirror planes. So this turns out kind of nice in that we can use carbon 13 to differentiate these specific constitutional isomers. Again, it's a very simplified case in that both substituents are the same. If the substituents were different, this number would then change. So don't commit this to your memory. You always have to do analysis for the specific compound. So I want to do this for proton over here. So maybe I need to erase and redraw. So we're going to do the same type of analysis. I just want to erase all this stuff so we have a cleaner picture to look at. So for the proton over here, for the ortho case, let's do it this way. How many unique sets should we have? And then after that, what is the ratio of the protons in those sets? So we want a couple numbers, number of sets, and then the ratio of those protons in each set. What should we do for the ortho case? How many unique sets do we have? So we got a couple of responses here. There are three unique sets in the ratio of them. So the methyl groups are a set, that's 6. So we're looking at the molecule. We have these, we're coming, there's none here. We come out, those are the same, that's 2. Then these are different, that's 2 as well. So we know that they're different because if you look, if we're tracing along the relationship of this CH to that, that's like a 1-2 relationship. And even though this is a CH, it's different from that because it's 1, 2, 3. So that's how we end up with 3 different sets. What about for, so maybe I'll write that in there, 3, 1, 1, 3, 1, 1. So you can see, and again, that has that mirror plane. So we get 6, 2, 2. What about for orthoxylene? How many sets, and then what are the ratios? So we have a couple of responses of 4, 6, 2, 1, 1. Again, this can be in any order just as long as you have like the total number. So if you add this, 6 plus 2 is 8, plus 1, 9, plus 1 is 10. That number has to equal this number here, because we're accounting for all of the hydrogens. So where do we see the 4? Again, we have a plane of symmetry. We have 1, 3, 1, 1. This one and this one, there's no mirror, so that's how they become by themselves. The 3 is mirrored here, that's where we get the 6. This 1 is mirrored there, so that's where we get the 2. Okay, lastly, finishing off with the paraxylene, how many sets, and then what's the ratio? So yes, there are 2 sets. And again, that ratio will be 6 to 4. So if we count 3, then we come down, there's none there, there's 1 here. That one is the same as this one. This one is the same as that one and that one. So these 4 are all the same type. And then this 3 is mirrored here. So that's where we get 6 to 4. And again, keep in mind that this exercise, we have the same substituent. If the substituents were different in those relationships, these numbers would also change. So let me erase this board. Trevor said he needs a review of NMR. So let's look at one of these. Let's look at one of these where we actually, instead of having the same substituent, we change it. How do the the peaks change? What are the multiplicities or the couplings at that point? So I'm going to go ahead and erase this. We'll look at one more NMR problem real quick. So while I'm thinking about this, I'll make an announcement in Canvas that links again the Office of the Registrar description of these new grades for this spring semester, so that if you did not want to report a grade that affected your GPA, you can convert it to one of these new letter grades. So I'll link that in Canvas. The other announcement I think that I sent out last week, if you have an assignment in Wiley Plus that was not started or not completed prior to the initial deadline, all those have reopened so that if you have unfinished problems, you can go back, finish them, and submit it prior to the end of the semester. If you've already done the work and you've looked at all the problems, the grade has been recorded, so you don't have to do anything. So what are we doing now? We're going to look at an example where the substituents are not equal. So say we have this compound so we have a bromine and a methyl, so we could name this one bromo, 2-methylbenzene. You could shorten that to bromo toluene. Toluene encompasses the methyl. The ortho tells you the relationship between the bromine and the methyl. So what we're looking at here, again, we want to do that exercise. For this molecule, how many unique carbon atoms are there? So yeah, this answer is 7. So again, remember when we had both methyl, we had 1, 2, 3, 4. Now the answer is 7. So each ring carbon is unique, and then the methyl carbon by itself is unique. So what about how many unique sets, and then what's the ratio for proton? So we have 5 sets. And then what about the ratio? So it's 3 to 1 to 1 to 1 to 1. So again, this number 5, if we count 1, 2, 3, 4, 5, that's our 5 sets. the total number 3, 4, 5, 6, 7. That's the total number of protons in the molecule. And this is the ratio between those 5 sets. So I want to dig a little bit deeper for this. We want to assign multiplicities now. So here's a methyl group. What should the multiplicity of the methyl group look like in the NMR? So maybe just use these designations. S is singlet, D is doublet, T is triplet, Q is quartet. So the methyl group should be what? The methyl is going to be a singlet. So again, when we're assigning multiplicity, we're using the n+1 rule to assign multiplicity. This carbon has 1 carbon that bears no hydrogens, so we have 0 plus 1. That gets us our singlet. This hydrogen right here should be what multiplicity? So this one's going to be a doublet. So this carbon has none. This has 1. We have 1 plus 1 is 2. That gets us our doublet. What about this one right here? That one's a triplet. So we have proton itself. So it's bonded to that carbon. We have 1 plus 1. 2 plus 1 is the triplet. So what about this one right here? So this one's also a triplet. And then finally this one. That's a doublet as well. So maybe we can just look at. Let's look at the other 2 isomers so that we can sort of see the differences again. How we can use these forms of spectroscopy to differentiate these isomers. And the reason I'm spending time on this exercise now, when you run the substitution reactions of a benzene ring, you can get mixtures of these different isomers. And so we can use the spectroscopy to explain which isomers are produced. So let me write so I'll leave the methyl group in the same orientation. I'm going to move the bromine now to the 3 position. So how many unique carbons do we have for now the meta isomer? So this is ortho, this is meta. How many unique carbons do we have for the meta? We have 2 7s versus a 5. The 7s are going to win. So each ring carbon is unique. The methyl is unique, so that gets us 7. So 6 plus 1 is 7. So the reason it's 7, you cannot have any mirror plane perpendicular to the structure that makes carbons similar to one another, therefore symmetric. So within the plane of this whiteboard, yes, there's symmetry, but orthogonal to it, there is not. So what about here? How many unique protons, and then how many unique sets, and then the ratios between them? So in your chat box, write the number for the unique sets and then the ratio. So based on the responses, this is going to be, again, 5 to 3, 5 unique sets, the ratio 3 to 1 to 1 to 1 to 1. Now, what I want you to pay attention to is look at these numbers now, 7, 7, 5, 5, and then the ratios. These are the same. So based on this thought experiment for this amount of data, we can't differentiate them. So what we need to do is look at the multiplicities then, because the multiplicities are going to help us differentiate the ortho from the meta. The methyl is still a singlet. What is this hydrogen going to be? So that's a doublet. So let me over here write singlet. So all I've done at the top here was take these multiplicities and then put them below. We have singlet, doublet. What about this hydrogen? Triplet. This hydrogen. And that's the doublet. And then the last hydrogen here should be what? Singlet. So now if we look at the multiplicities, we have 2 doublets, 2 triplets. We have 2 doublets, a triplet, and a singlet. So the multiplicities allow us to differentiate between the ortho and the meta at this point. Let's go ahead and finish with the para. Sort of squeezed for space here, but we'll draw it right here. So this is the para-isomer. So it's the 1,4 relationship. How many unique carbons do we have? Okay, so this is 5. We have 1, 2, 3, 4, 5. How many unique sets of hydrogen do we have, and then what are those ratios? So we have 3 sets. Then the ratio is 3 to 2 to 2. So we can see 775 from a rough approximation. If you were given a spectrum, you would count the number of peaks in that carbon. If it was 5, it would be this. If it was 7, it could be one of these. So we can sort of use spectroscopy to differentiate the para from the meta and the ortho. So again, here, the methyl is a singlet. Those H's are the same. And then these H's are the same. So these H's should have what multiplicity? Yeah, they'll be doublets. So again, this exercise is meant for you as a thought experiment before you actually see spectra, to differentiate them based on unique carbon and unique sets of protons. And again, the big picture of this is when we start learning the reactions, you can get different product distributions of the benzene relationships. So the way that you tell what you got from that reaction is through this sort of analysis. So any questions before we move on? So I'll go ahead and erase this this board. So this next board will probably take us 15 minutes or so to get through, and there's a certain logic that's going to be presented here to convey to you the reactivity of benzene. So this is benzene. Benzene undergoes substitution reactions. So when we take benzene and we treat it with an electrophile, the hydrogen is substituted for the electrophile. So now we've ended up with a monosubstituted benzene. And this ties back into the original whiteboard we went over. Depending on what that electrophile is, if it's electron donating, and we do a second reaction now on this substrate, if it's electron donating, the second substituent will either go ortho or para. If the substituent is electron withdrawing, then it can only go meta. So you need to be able to classify, is the substituent electron donating or is it electron withdrawing? These are the possible scenarios for those di-substituted isomers. So again, this is ortho, this is para, this is meta. And that's just the relationship 1,2, 1,4, or 1,3 between the substituents. So now the point I want to make, I want to convey to you, why does benzene undergo a substitution of H for the electrophile rather than an addition to the pi bond? So the next board we're going to look at is heat of hydrogenation to understand why this is. And so just bear with me as we sort of trudge through this logic that will help us understand, again, what the word aromatic means as well. So we're going to look at heat of hydrogenation. Of alkenes again, specifically cyclic alkenes. So let me start with the first one. If you take cyclohexene, and you add one equivalent of hydrogen, you get cyclohexane. So in red marker, I'm going to write a number. So you run the reaction. When this happens, what this number negative means, the hydrogen adds across the double bond, you hydrogenate it, and then it's releasing this much heat, 120 kilojoules per mole of heat. So that's telling us that the reaction is exothermic. Now, if we take the following molecule, (1,3) cyclohexadiene, plus 2 equivalents of hydrogen, so 1 here and 1 here. We're forming the same molecule. This is releasing 232 kilojoules per mole of heat. Now this is sort of the tricky part to understand. So notice we have 1 double bond, we have 2 double bonds. The next molecule has 3 double bonds. Now, if we were to think of this instead of benzene, but we think of it as 1, 3, 5 cyclohexatriene as a theoretical molecule. And we use these numbers. We have 3 pi bonds, 1, 2, 3. We need 3 moles of hydrogen. If we just take 120, so 120 per mole of H2, multiply it by 3. We do the hydrogenation to get cyclohexane. This theoretical molecule should evolve this much heat, right? So again, we carry this reaction out, that much heat is evolved. If we use 3 equivalents of H2, 3 times this gets us that. But experimentally, you don't observe that. And so, again, this would be a theoretical molecule where we're not talking about things being conjugated. So when we actually run this experiment, and benzene is reduced to cyclohexane, we can do that. This actually evolves negative 208 kilojoules per mole. So this difference here so the difference between the 360 and the 208 that difference is called resonance stability. And because it's due to benzene, historically, that's what organic chemists term as aromaticity. Again, the 360 is what it should be if it were just 135 cyclohexatriene with no conjugation stabilization. The molecule itself, benzene, actually evolves this much heat. We arrive at this number as the difference between the two. And what we observe between what it should be, that's known as the aromaticity, which is ascribed to resonance stabilization. So what this is going to lead into, and what we saw from 255, is that a typical pi bond undergoes addition reactions. When we do an addition reaction, we're adding something here, and the double bond goes away. We saw a couple lectures ago with these dienes, we can add like HCl, and we get either kinetic or thermodynamic addition. With this molecule, benzene in particular, it does not undergo addition. So let me erase some of this and show you that with some structures. Before I do that, any questions on resonance stability here? So this is a pretty long way of saying benzene undergoes substitution and not addition. So just to show you, that's an addition reaction. If you took benzene and treated it with HCl, addition reactions do not happen with benzene. So the X over the arrow means no reaction. And again, I want to harp on this point. We view this, the pi bond here is a normal double bond that undergoes addition. These pi bonds are not normal pi bonds. And again, the reason for that is when they're in this arrangement in the six-membered ring, the stabilization leads to aromaticity. If you were to do an addition reaction, it breaks the aromaticity. So it's thermodynamically unfavorable to do addition. So benzene undergoes substitution reactions. A hydrogen gets substituted for some electrophile. So let me state that another way. So here's benzene. This is our electrophile. I'm drawing it this way to show that E is the electrophilic component. A is going to be some sort of leaving group that is a conjugate base of the original acid. So what's going to happen? The H is substituted for the E. So this retains aromaticity at 150 kilojoules per mole of resonance stabilization. As opposed to what you saw in 255, what I showed you on the prior board. Benzene does not undergo addition. Because then that loses the aromaticity or the resonance stabilization. So in this reaction, which we are focused on, an H is substituted for an electrophile. So if this is the electrophilic component, benzene is the nucleophilic component. So if you're just starting with benzene, you have 1, 2, 3, 4, 5, 6 equivalent hydrogens. So if you do a substitution, it doesn't matter which one you substitute. Where it gets complex and what we'll spend a lot of time in the next couple lectures, if you already have an existing substituent, how is that substituent going to direct the next reaction? For example, that would be an ortho para-director, or alternatively, a meta-director. And so that's what we'll spend time learning. In the next couple of lectures. But first, what I want to do is look at the mechanism of how this happens. How does the H get substituted for the electrophile? So we're going to put up a reaction coordinate diagram and look at the individual steps that occur. The board's getting a little crusty here. Okay, so I'm going to title this Mechanism of Electrophilic, Aromatic, Substitution. Abbreviated EAS, Electrophilic Aromatic Substitution. So remember in module 2, where we saw nucleophilic acyl substitution. So all these different mechanisms have these abbreviations, and you should be familiar with them, you know, as we finish out the second semester here. So I think what I'm going to do is I'll probably have enough space to just draw the mechanism here, and then on a second board I'll draw the reaction coordinate. I don't think there's enough room here. So step 1. Again, we have benzene. I'm just showing one of the H's here. I'm using a very generic electrophile. The pi bond is acting as the nucleophile to attack that electrophile. So pi bond, the arrow starts, it's pointing towards the electrophile. We then break this bond. Now we're substituting this hydrogen. So maybe I'll just circle that through. So if we're substituting that hydrogen, that's the bond we're making. This carbon ends up with a plus. And then we have the conjugate base of that electrophile that we started with. So this is the slow step. the slow rate determining step. The reason this step is slow is because we're starting with benzene, which is aromatic. We're then putting this plus charge in there. It disrupts the aromaticity. So these structures, these resonance forms I'll draw, these are all non-aromatic. So I'm just showing resonance forms. So again, that's step one, the slow step. Slow because we lose the aromaticity. Step two. Step two is basically going to be where this conjugate base abstracts the proton and does an elimination. So we can think of, in terms of the individual steps, we have the pi bond acting as the nucleophile to add in the electrophile, and then the second step is elimination, which restores aromaticity. So you can think of this next step as like an acid base or a proton transfer step. We have a pair of electrons. We're going to abstract that hydrogen. So maybe proton transfer or elimination. We can use a lot of different terms to describe what's happening. This restores the aromaticity, and this is fast. So there's the hydrogen that we've abstracted. I've circled it throughout so you can see its movement. And so now we end up with a monosubstituted benzene ring. So looking at the time, we're about out of time. We have a minute left. So what I want to start with next time is the actual reaction coordinate. This bottom thing here that I'm showing. I want to draw that up there and go through it, sort of to show you again transition states, intermediates, and what we mean by slow and fast. So we'll pick up with that on Wednesday. I'll post that link to the new grading scheme the university has, and try to work on your homeworks 9 and 10. Your exam 4 bonus, and the quiz, I have the quiz 4 out of it to populate. We'll have office hours tomorrow as well through the Canvas conference. Again, if you have any questions or anything, just shoot me an email. But other than that, I'm going to go ahead and close out the live stream for today, and it will be posted on YouTube later tonight. So we'll see you all Wednesday.